Okay, in this video, we're going to be looking at the 1998 AB Calculus exam. So in this video, I'm going to show you all the problems, the solutions, and where you would get each point. So I'd recommend that before you solve it, before you watch the video, you try to solve it yourself, and you can count how many points you would have gotten if you had been taking the test real time. So let's look at the first problem. So we have R being the region bounded by the x-axis, the graph y equals square root of x, and the line y equals 4. Even though these are pretty simple things, it's still a good idea to draw a sketch. So let's draw the graph of y equals square root of x, something like that. The x-axis is here, and the line x equals 4 is a vertical line here. So this is the area that we're talking about, that we want to do stuff with. So in part A, we're asked to find the area of the region R. Okay, so the area is going to be the integral from here to here, and since we're dealing with x, it's going to be going from 0 to 4. So it's the integral from 0 to 4 of the square root of x dx, and this is your first point for setting this up. And then next, we're gonna evaluate this integral by first, instead of writing square root of x, I'll write x to the 1/2, and then I need to add 1 and then multiply by the reciprocal. So it's going to be 2/3 x to the 3/2, and the bounds are 0 and 4. So plugging in the bounds, it's going to be 2/3 times square root of 4 is 2, 2 times 2 cubed is 8, which is 16/3. And getting this correct answer would be your second point. Okay, now let's look at part B. For part B, we need to find the value of h such that the vertical line x equals h divides the region R into two regions of equal area. So now, since we know the total area is 16/3, we know that the half area is going to be equal to 8/3, right? So we can use that information, and we'll say, alright, so we want to find out the integral from 0 to some value h, such that the integral of square root of x dx equals half of the area, so it equals 8/3, right? So what's the value h such that the area is half of the total area? And your first point would come from setting this up. Okay, and then let's evaluate this the same way we did. We'd get 2/3 x to the 3/2 evaluated from 0 to h, and then if I plug this in, I'm gonna get 2/3 h to the 3/2, and remember this is still equal to 8/3. So now it's just solving this equation for h. The 3's are gonna cancel. The 2 and the 8 are gonna make a 4. So h to the 3/2 equals 4, and then raise everything to the 2/3 power to get h is equal to 4 to the 2/3. There are some alternate forms of this, but if you got the same answer, you'll be fine. And getting this correct number would be the second point. Alright, now let me erase and we'll do the next part. Okay, part C. Find the volume of the solid generated when R is revolved around the x-axis. So this is the x-axis, and since our curve is touching, or the area we want to rotate is touching the x-axis, we only need to have one radius, and that radius is going to be this distance here, which is just square root of x, right? It's kind of hard to see, but square root of x. So that's going to be pi times the integral from, again, the bounds are still 0 to 4, right? Because we're still dealing with x. So from 0 to 4 of the radius squared, so square root of x squared dx. And if you just wrote this, you'd automatically get 2 points. One for getting the constant pi and the limits 0 and 4, and the second point for getting this part inside the integral, the square root of x squared. So just this, we didn't even evaluate anything yet, and we already have 2 points. Okay, so evaluating this is going to get pi times the integral of 0 to 4 square root of x squared is just x, and then this is x squared over 2 from 0 to 4, which is just 4 squared is 16. 16 over 2 is 8, so it's 8 pi. And the 0 is going to just make that 0. So getting this correct answer would be your third point. And then now let's look at part D. Part D says that the vertical line x equals k divides the region R into two regions such that when these two regions are revolved around the x-axis, they generate solids with equal volumes. Find the value of k. Okay, so this is going to be similar to the method we used in part B. So we know that the total volume is 8 pi. So we want to find half the volume, which is going to be 4 pi. So there's going to be some number, k, such that the integral from 0 to k of square root of x squared dx is going to be equal to half of the total volume. So half of 8 pi is 4 pi. So the question is, what's the value of k for this? And we'd get 1 point for setting this up. And then the pi's are going to cancel. And then evaluating this is going to give us x squared over 2 from 0 to k being equal to 4. Plugging in k gives us k squared over 2 equals 4, and k is square root of 8. So getting that answer would be the second point. And that's it for question 1. Let's look at question 2 now. Okay, question number 2. We have this function, f of x is 2x e to the 2x. We've got to find these two limits first. So we need to find the limit as x approaches negative infinity of 2x e to the 2x. And you'll notice if I plugged this in directly, if I plugged in negative infinity, I'd get negative infinity times e to the negative infinity, which is 0. And this is one of the indeterminate forms, which allows me to use L'Hopital's rule. But if you remember, if we want to use L'Hopital's rule, we have to have a function in like this kind of form. We would have f of x over g of x. So we don't have something over something else. And so that means we need to rewrite this function in a way such that it follows this form. So we're going to do that by taking this e to the 2x and using their exponent rules. We can rewrite this as over e to the negative 2x, right? If I make the exponent negative, I need to bring it to the bottom. And then now I have something over something else, which allows me to use L'Hopital's rule, take the derivative of the top and the bottom separately. So I'm going to get the limit as x approaches negative infinity of 2 over negative 2 e to the negative 2x. These are going to cancel, and that's going to give me 1 over, well, the negative and the negative are going to make positive infinity. So 2 over e to the positive infinity is 2 over infinity, which is 0. Okay, that's the correct answer for the first part of part A, and that would get you 1 point. And then for the second part, we want the limit as x approaches positive infinity of 2x e to the 2x. This is a lot simpler. We just plug in infinity, I guess. We get infinity times infinity, which is infinity. Okay, and this would make sense because the entire function here is increasing without bound. It just goes up and up and up and never stops. So it does make sense that the limit as x approaches infinity would be infinity. Okay, let me just erase this stuff and look at part B. Okay, part B. Find the absolute minimum of f. Justify that your answer is an absolute minimum. Okay, so if you remember, to find the absolute minimum of a function, we need to first take its derivative, set it equal to 0, and use that to find the critical numbers, right? So let's start by taking the derivative of f of x, f prime of x. And then now you'll notice we have like two parts. We have this part, you have this part. So two functions being multiplied together. That means product rule. So we'll have the first function, 2x, times the derivative of the second function. The derivative of e to the 2x is 2e to the 2x, plus the second function, e to the 2x, times the derivative of the first function, 2. This is, I can pull out the 2e to the 2x. I'm going to get 2e to the 2x times 2x plus 1, right? And so on a separate line, that's really important, do this stuff on a separate line. I'm going to take what I just wrote and set it equal to 0 to find the critical numbers. And this first part here, this will never equal 0, because e to the, when you have something being raised to the x power, it's always going to be positive, right? So I can just like ignore this section completely and just focus on the other section here. So 2x plus 1 equals 0, x is equal to negative 1/2. This makes our derivative 0. This is a critical number, so we can test whether it's a minimum or a maximum by putting it on this line here, number line. We can have negative 1/2. If I put in a number greater than that, if I plug in like, 10,000 for example, I'm gonna get a positive number. If I plug in a negative number like negative 10,000, I'm gonna get a negative number, which means the graph is decreasing, then it's increasing. So this is a relative, or an absolute minimum in this case, because it's the only critical number on the graph. Okay, so now what that means is, so the question is not asking for what the x value of the absolute minimum is. It's asking for the absolute minimum. So now that we've found the x value, 1/2, right? This is the x value where the minimum value occurs. I need to plug this back into the function, and the output is the minimum value, right? So the minimum is f of negative 1/2, which is, if you remember, f of x is 2x e to the 2x, so that's 2x times e to the 2x. This cancels, and I get negative 1/e. Okay? In this problem, for the points, you would have gotten, I forgot to mention it, you would have gotten one question for finding x is equal to negative 1/2 and like setting it up this way by setting the derivative equal to 0. And you would have gotten another point for the 1/e part. And then the final point would have been in the justification, because it says justify that your answer is an absolute minimum. And the way that we're going to do that is, I'm not going to write it out because it's going to take a while, but what you'd say is, you'd say, okay, negative 1/e is the absolute minimum of f of x, because f prime of x is less than 0 for x is less than 1/2, and f prime of x is greater than 0 for x is negative 1/2. Therefore, f of negative 1/2 or negative 1/e is the absolute minimum. Something along those lines would have been correct. Okay, now I'll just erase all this stuff and look at the next part. Okay, part C, real quick, the range of f. Remember how we found that the minimum, the minimum is negative 1/e? Well, that means that this is the lowest that it can go. And then what's the maximum? Well, remember how we said in part A that f of x is a constantly increasing function. It increases without bound, just keeps going up and up and up. So as x gets bigger, f of x gets bigger. So I mean, it's never going to reach like a maximum number. It's just going to go on to infinity. And then putting this together to get my range, it's going to be from negative 1/e to infinity. And then since it can reach this value, put a brackets, and just as a matter of how it's done, you put comma for infinity. So this is the range. You get 1 point for that. Real quick, simple. And let's look at part D. So for part D, we have to consider the range of functions defined by y is equal to bx e to the bx, where b is a non-zero constant. Show that the absolute minimum value of this is the same for all non-zero values of b. Okay, so even though this looks a lot more complicated, they added this like other random variable here, b. We're going to approach the same way we did with part B, and we'll find it's really not that bad. So first, remember, absolute minimum means taking the derivative, setting it equal to 0. So we'll start with taking the derivative f prime of x, and that's going to be, again, so notice we have like two parts here. We have b to the x, and we have e to the bx. So we're going to have b to the x times the derivative of e to the bx, which is b e to the bx. And then we're going to add e to the bx times the derivative of bx, which is b. I can pull out the b e to the bx on both sides, and I'm going to get b e to the bx times 1 plus bx, right? And I want to set this equal to 0 on a new line, equals 0, and just like before, this will never equal 0 because it'll always be positive, and or negative if b is negative. And 1 plus bx, that's the only thing that can be 0. So 1 plus bx equals 0. X is going to be negative 1 over b. And you would get 1 point for setting this equation up, 1 point for getting your answer of negative 1 over b. And then finally, remember, we want to find the absolute minimum. It says the absolute minimum value, right? Not the x value, just says value. And when it says like that, that means you want to find the f of that. So f of negative 1 over b. And let's go up and look at the function one more time. F of x is bx e to the bx. Let me write that here real quick. Bx e to the bx. So plugging in negative 1 over b gives me b times negative 1 over b times e to the b times negative 1 over b, and the b's cancel, this gives us negative e to the negative 1, or negative 1 over e, which is our final answer. We found the absolute minimum, and notice that no matter what the value of b is, as long as b isn't 0, we get the same minimum value of negative 1 over e. So you get the third point for solving that and getting your right answer. Okay, that was question 2. Now let's move on to question number 3. Okay, so we're given here in question 3 the velocity of a car as a function of time, and we also have a data table with different velocities at different times. And in part A, we're asked during what intervals of time is the acceleration of the car positive. So we don't have acceleration data here, we only have velocity data. So we need to somehow relate acceleration to velocity. And the way we do that is that if the acceleration is positive, then the velocity is increasing. What that means is that it's a positive slope, it's going up. So we can look on this velocity graph, and whenever it's increasing, whenever the velocity is going up, we're going to have a positive acceleration. So it looks like we're going up here, we're going up, and then here we stop and we're going down, and then in 45 we go back up again, right? So it looks like on the interval 0 to 35, and on the interval 45 to 50, the acceleration is positive, right? And the reason for that, they're asking for a reason for your answer, which is just going to write one sentence. You'd say, well, the velocity is increasing on the interval 0 to 35 and 45 to 50, therefore the acceleration is positive on those intervals. And the points here would come from, you get 1 point for the 0 to 35 part, get another point for the 45 to 50 part, and you'd get a third point for explaining it properly. Okay, now let's look at part B. Find the average acceleration of the car in feet per second squared over the interval t from 0 to 50. So we're going to have to use the equation for the average value of a function. So what that's going to be is, it's going to be f of b minus f of a over b minus a, where a and b are your starting and finishing points. And here we're starting at 0 and we're going to 50. So this is going to be v of 50 minus v of 0 over 50 minus 0. Remember, this is the average acceleration of the car, and the way we're going to get v of 50 and v of 0 is by looking at this chart here. If we go to t equals 50, the velocity is 72. And if we go to t equals 0, the velocity is 0, minus 0, over 50 minus 0, which comes as, I'm just going to say it's 72 over 50, and the units are feet per second squared, as you can see here. So that's the answer for part B. You just get 1 point for getting the correct answer, that's all. And then for part C, we need to find one approximation for the acceleration of the car at t equals 40, so the instantaneous acceleration. And now there's a bunch of different ways to do this based on how you decide to approximate. The way I'm going to do it is, since we're trying to find the velocity at the acceleration at t equals 40, I'm going to take t equals 35 and t equals 50. I'm going to use those as my endpoints, and then use that to find the average acceleration. So v of 45 minus v of 35 over 45 minus 35. Like I said, there's a bunch of different ways to do this. This is just the way I'm doing it. You could get a slightly different answer depending on how you do it. Again, v of 45, we're going to look at the table 60. V of 35, look at the table 81. Over 45 minus 35, which is negative 21 over 10. And the units are, again, feet per second squared. You might have gotten like negative 3 or something. It's all okay as long as you did the correct method. It's supposed to be part C. I don't know what I'm doing there. And you'd get points here. You'd get 1 point for writing this kind of an equation and setting this up, and you'd get another point for your right answer. Okay. Finally, part B. Approximate the integral from 0 to 50 of the velocity as a Riemann sum. So they're just asking us to approximate the area under the curve here from 0 to 50 using a Riemann sum with midpoints of 5 subintervals of equal length. So since we're going from 0 to 50, if we're going to split this up into 5 different groups, each group is going to be 10 in length. So the midpoint formula for, I'm going to do it down here so I have a bit more space. For the midpoints of 5 equal subintervals, it's going to be the base, which is 10, right? Because we're going from 0 to 10, 10 to 20, times the velocity at the average of the first 2 points. So the average between 0 and 10 is 5, plus the average of the second 2 points. It's going to be from 10 to 20 is 15. And we're going to go on, 25, 35, and finally it's going to be between 40 and 50, so 45. Okay, and then all of these are going to come straight from the table. It's going to be 10 times v of 5 is 12, and we have 30 plus 70 plus 81 plus 60, and if you add that up and multiply, you're gonna get 2,530 feet. And the reason feet is our units is since we're finding the area under the curve, we're gonna multiply the 2 units, so we'd have feet per second times seconds, which just gives us feet, so that's our units, and that's our answer. The points here, you'd get 1 point for writing this midpoint equation out, and you get another point for the right answer. And then the third point would come from explaining the meaning of this integral, and when we're integrating velocity, we're going to get distance, and since we're going from 0 to 50, we're talking about the distance the car traveled totally in feet over the first 50 seconds. So from t equals 0 to t equals 50, this integral is the total distance the car traveled across that time. Okay, that's question 3. Let's go on to question 4. Okay, so in question 4, let f be the function with f of 1 equals 4. So already we can say, alright, we have the point 1, 4, such that for all points x, y on the graph of x, the slope is given by 3x squared plus 1 over 2y. Now remember, the derivative is just the slope at a point. So when they're giving us the equation for the slope, they're giving us the equation for the derivative. So what that means is dy dx is 3x squared plus 1 over 2y, right? They're giving us the equation, the differential equation for this function f. And then part A, we need to find the slope of the graph at f, for f at the point where x equals 1. So when x equals 1, since we know that this is 0.14, we know that when x equals 1, y equals 4, right? So since we want to find the slope of this line at 1 comma 4, we can just plug in 1 and 4 into our slope formula, our derivative, and that'll give us our answer. So we want the slope of the graph at the point 1 comma 4, which is going to be 3 times 1 squared plus 1 over 2 times 4, which is 3 plus 1 over 8, which is 1/2. And in this part A, you get 1 point for your correct answer. That's all. In part B, what do we have to do? We have to write an equation for the line tangent to the graph of f at x equals 1, and use that to approximate f of 1.2. Okay, so what that means is we need to write an equation, and that's going to be in point slope form. Point slope form, if you remember, is y minus y1 equals m times x minus x1. And to be able to write an equation in point slope form, you need the slope of the line, and you need 1 point. And if you remember, in part A, we did exactly that. We found the slope of the line given 1 point. So we can take the point 1 comma 4, we can take the slope 1/2, and use that to write the equation for the derivative at x equals 1. So at x equals 1, we know that y minus, and then y1 is 4, equals m is the slope of the derivative, which is 1/2, x minus, and then the x point is 1, and that is our, well, that's our equation. So it's like, I guess you can say half of our answer. And then remember, they also wanted us to use this to approximate f of 1.2. So when x is 1.2, what is y approximately equal to? Well, I can just plug in 1.2 in here for x. So we'll get y minus 4 equals 1/2 times 1.2 minus 1. So y is equal to 1/2 times 0.2 plus 4, which is 0.1 plus 4, which is 4.1. And this is where the other point would come from for part B. Okay, let's look at part C real quick. Okay, so part C. Find f of x by solving the separable differential equation with the initial condition f of 1 equals 4. So now we know that we have this equation here, and when it says solve the separable differential equation, we need to bring all the y's to one side and bring all the x's to the other side. So let's first multiply everything by 2y. I'm going to take the 2y and bring it over there. So 2y dy. And then to bring all the x's onto one side, I'll take the dx and bring it over here. So I'll get 3x squared plus 1 dx. And then now, since we want to, once we separate it like this, we need to integrate both sides. And so the integral of 2y is y squared. And then the integral of 3x squared is x cubed. The integral of 1 is x. And then don't forget the plus c, since this is an indefinite integral. And how do we find the value of c? Well, since f of 1 equals 4, I can plug in 1 comma 4 in here. So it's going to give me 4 squared is equal to 1 cubed plus 1 plus c. 16 is equal to 2 plus c, and 14 is equal to c. And putting that back into my original equation gives me y squared is x cubed plus x plus c. And then, we know that c is 14, so I can write 14 there. And then taking the square root of both sides, I'll get y is equal to plus or minus square root of x cubed plus x plus 14. And the question is it plus or minus? Well, since our point was 1 comma 4, and it's so when x is 1, y is positive, that means it's going to be the positive square root. So y is equal to the positive square root of x cubed plus x plus 14. That was that. So they asked us to find f of x, so we found f of x by solving the separable differential equation. So this gave you a lot of points, actually. You get 1 point for separating it, like by bringing the y's on one side and the x's on the other side. You would get 1 side for properly integrating y. You'd get another point for properly integrating x. You'd get another point for solving for the constant c. And you'd get a 5th point, I think. Yeah, 1, 2, 3, 4, 5, by solving the equation for y by plugging in c and taking the square root. So that one part had 5 points. So now for part D, use your solution from part C to find f of 1.2. So that's going to be simply plugging in 1.2 into this equation. So y is equal to square root of 1.2 cubed plus 1.2 plus 14. And if you put that in your calculator, you'd get, this is approximately equal to 4.114, and you'd get 1 quick point for that, just plugging in. Okay, so that was question number 4. Now let's move on to the final question. No, next there's 2 more questions. Okay, so question 5, not the last question. We have the temperature outside of a house in a 24-hour period given by this equation, and first we need to sketch this graph. So, part A, before we start actually sketching, let's take a general guess on what this shape is going to look like by looking at this equation. So we have a negative and then a cosine. So we can say that this is probably going to look like a negative cosine graph. And if you remember, a positive cosine graph looks something like this. So a negative cosine graph, instead, is going to look like the opposite of that. It's going to look something like this. Right? That's going to be the general shape of our graph, like a bell curve. And then I can get some specific points by plugging in values of t into this equation. That'll make it easy to solve the cosine. So if I plug in a multiple of 12 for t, or if I plug in 0, that's going to give me some really easy numbers. So I'm going to plug in t equals 0, t equals 12, and t equals 24, which will easily allow me to calculate f of t for those 3. And then that information, combined with the general shape of the graph, is going to give us the answer. So let's start by first plugging in 0 into this equation. F of 0 is 80 minus 10 cosine. If I plug in 0 into here, I'm just going to get 0. Just 80 minus 10. Cosine of 0 is 1, so just 80 minus 10, which is 70. And if I plug in 0, I get 70. So this is the point 0 comma 70. And then if I plug in 12 for t, it's going to be 80 minus 10 cosine. And then if I plug in 12 for t, it's going to be the 12 and the 12 are going to cancel. So let's get cosine of pi. Well, cosine of pi is negative 1. So it's going to be minus negative 10. So plus 10, or 90. And that gives me the point 12 comma 90. And then finally I'll plug in 24. So that's going to be 80 minus 10 cosine. Plugging 24 here, I'll get 24 over 12, which is 2. It's cosine of 2 pi. And then cosine of 2 pi is the same thing as cosine of 0. It's 1. So we'll just get 80 minus 10, or 70. That's going to be 24 comma 70. So I have the general shape. I have these 3 points. And let's just plot those points on our graph here. So if t is 0, f of t is 70. 0, 70, right here. And then 12, 90. So when t is 12, f of t is 90. And then when t is 24, f of t is 70. t of 24, f of t is 70. And then I have this general shape of the graph. So I'll just try my best to draw like a rough, rough sketch. That's terrible. But it's fine. That's the general shape. It's like a bell curve with these 3 endpoints and this one maximum here. Okay, and let's look at part B. Oh, before we move on, I forgot. We get 1 point for like drawing this graph correctly. Okay, part B now. Find the average temperature to the nearest degree Fahrenheit between T equals 6 and T equals 14. So the way we're going to do that is we're going to say, okay, this is the formula for the average value is 1 over b minus a times the integral from a to b of f of t dt. And then I can plug in, since we're going from 6 to 14, a is 6 and b is 14. So now it's just going to be a matter of plugging in numbers, right? So this is 1 over 14 minus 6 is 8. So 1 over 8 times the integral from 6 to 14 of f of t, so of this stuff, of 80 minus 10 cosine pi t over 12 dt. And then this is just going to be evaluated in the calculator, and you're going to get an output of about 87.162 degrees Fahrenheit. And in terms of points for this section, you'd get 1 point for the limits, 6 and 14, and for including the 1/8 down here. You'd get another point for the stuff that's inside the integral, but for plugging in f of t into here. And then you get a third point for the right answer of 87.162. Okay, now let's look at part C. An air conditioner cooled the house whenever the outside temperature was at or above 78 degrees Fahrenheit. For what values of t was the air conditioner cooling the house? So for what values of t was f of t greater than 78? Right, so we want to find when is f of t greater than or equal to 78. So if we just plug in 80 minus 10 cosine pi t over 12 for f of t being greater than or equal to 78, and then solving for cosine of pi t, subtract 80, divide by negative 10, cosine of pi t over 12 is less than or equal to 0.2 you get. And then this is just going to go in the graphing calculator. You graph this on y1, this on y2, find the intersection points, and you'd get that this is true when t is between 5.231 and 18.769. So this is the t values for when the temperature is above 78. You would get 1 point for setting up the inequality and 1 point for the answer. Okay, and then finally part D. The cost of cooling the house accumulates at a rate of 5 cents per hour for each degree the outside temperature exceeds 78 degrees Fahrenheit. What was the total cost of heating the house? Alright, so this is one of the more trickier parts. So we want to find out how many degrees above 78 was the temperature at any given moment. Right? So that would be the temperature, 80 minus 10 cosine pi t over 12. This is the temperature minus 78. This expression is going to give me how many degrees above 78 the temperature is. Right? And then I know that from part C, I know that the temperature is above 78 for 5.231 to 18.769. So this is the interval for when t is greater than 78. This is how much greater than 78 it is. So now all I have to do is I have to set up an integral from 5.231 to 18.769 of 80 minus 10 cosine pi t over 12 minus 78 dt. And the one last thing is, this is how many degrees it would be, and then we know that it's 0.5 cents, or yeah, no, $0.5 per hour. So to get the total cost, I'm going to take the number that I get from here, I'm going to multiply it by 0.05. Right, this is the hours, and then this is the cost per hour, so it's going to give me the total cost. And if I put this whole thing in the calculator, I'd get 5.096. And then if I were to round it to the nearest cent, this would be $5.10. And the point distribution here, 1 point would come from setting up the integral with the 0.05 on the outside. The second part would come from the stuff that's inside the integral, the integrand. And that was it. That was part 5, and now we'll move on to actually the last question. Okay, so we have a curve defined by all this stuff here, and in part A, we need to show that dy dx is equal to this. Okay, so we're given the derivative, we just need to prove it. So let's take the derivative of this function here. So since there's x's and y's all scattered together and mixed up, we're going to have to use implicit differentiation, meaning I'll just have, whenever there's a y, I'll just add a dy dx on the end. So this here's going to be 6y squared dy dx plus, and then here I'm going to have to use the product rule. So first I'll keep the 6x squared, and then take the derivative of y, which is dy dx. And then next I'll keep the y, and I'll take the derivative of 6x squared, which is 12x times the y, of course. And then the derivative of 12x squared is just the normally negative 24x. And then the derivative of 6y is 6 dy dx, and the derivative of 1 is 0. Solving this equation, we're going to take all the dy dx's and factor them out. And then these terms, they don't have a dy dx, so I'm going to move them to the other side. So if I do that, I'm going to get dy dx times 6y squared plus 6x squared plus 6 equals 24x minus 12xy. And then we're solving for dy dx, so I just need to bring this whole thing down. So I'll get dy dx is 24x minus 12xy over, that's a y, 6y squared plus 6x squared plus 6. And then finally, since everything here is a factor of 6, or multiple of 6, I'm going to divide everything by 6. So it's 4x minus 2xy over x, or y squared plus x squared plus 1. And if you'll notice, that's exactly what they have up here. So we proved that the derivative is equal to whatever they said it was. And then in terms of points, you'd get 1 point for setting up this implicit differentiation here, and you get another point for the correct final answer. Okay, so part B, we need to write an equation of each horizontal tangent line to the curve. So at the horizontal tangent line, the derivative is going to be 0. So 4x minus 2xy over x squared plus y squared plus 1. That's part B. So this is equal to 0. And then since the denominator can never be 0, we're not even going to worry about that. We don't care about that. We're just going to focus on the numerator and look at when the numerator is equal to 0. If I factor out 2x from both sides, I'll get, or from both parts, I'll get 2x times 2 minus y, 0, which gives me x equals 0 and y equals 2. And then to get the equation of the tangent line, I don't just want the points, I want the equation. Let's start with y equals 0. And I'm going to solve for, take this x equals 0, I'm going to solve for y. So if I solve for y, I'm going to get, taking 0, putting this into my curve to get the y coordinate. So it's going to be 2y cubed plus 0 minus 0 plus 6y equals 1. And if you solve this for y, you'd get y is 0.165, right? And then since the slope is 0, you get y minus 0.165 is equal to 0 times x minus whatever. So the entire equation is just y is equal to 0.165. So that means this is the equation for the tangent line at the point x equals 0. And then now let's move down a bit and try to find the equation of the tangent line when y equals 2. You might be asking, well, isn't that just y equals 2? Well, it could be, but we need to check that it's valid, that y equals 2 is a valid y coordinate. So that means we're just going to plug in y equals 2 into the curve and check what the x value is going to be. So if I plug in that, I'm going to get 2 times 2 cubed is 8. 8 plus 6x squared times 2 minus 12x squared plus 6 times 2, which is equal to 1. And then 8 times 2 is 16. 16 plus 12 is 28. So 28 plus 12x squared minus 12x squared equals 1. I'll subtract 28 from both sides, and I'll get 12x squared minus 12x squared equals negative 27. Well, 12x squared minus 12x squared is just 0. So it's 0 equals negative 27. And that's not true. So y equals 2 actually has no solution, because there's no x coordinate that'll make y equal to 2. So y equals 2 is not a valid solution, meaning this, where x equals 0 and y is equal to 0.165, this is the only solution. So y equals 0.165 is the only equation for the horizontal tangent line to the curve. And then in terms of points here, we would have we'd have 1 point for setting the derivative equal to 0. We'd have another point for solving the derivative equation. We'd have a third point for plugging in x equals 0 and finding the corresponding y value. And we'd have a fourth point by plugging in the y value and figuring out that the x value is not possible, so there wouldn't be a solution there. Okay, now let's look at part C. Okay, part C. The line through the equation with slope equal to -1 is tangent to the curve at point P. Find the x and y coordinates of point P. So through the origin means the line passes through 0, 0, and then slope -1, m is -1. I can use this information to find the equation of this line. So y minus 0 is equal to -1 times x minus 0. So y is equal to -x. And then this is tangent to the curve at point P, right? So at point P, this equation, y equals -x, and the 2y cubed plus 6x squared y minus 12x squared plus 6y. So at some point P, these two curves intersect. So what I'm going to do to find that point is I'm going to plug in -x whenever I see a y. I'm going to combine these two equations to make everything in terms of one variable. So it's going to be 2 times -x cubed plus 6x squared times -x minus 12x squared plus 6 times -x equal to 1. And now if you solved this equation for x, you would get x is equal to -1/2. And then since y is equal to -x, y is equal to negative of -1/2, which is just positive 1/2. And then that means the final point is going to be -1/2 comma positive 1/2. Right, that's the answer. Okay, so that was the entire AB 1998 test. Hope you found this video helpful, and yeah, that's it. Goodbye.